All right, everyone. Today we're going to talk about a common challenge we face in practical projects. We often encounter some tricky problems. Where do they usually come from? They often come from model repair. Model repair and model reconstruction are workflows we frequently encounter. During projects, these situations typically arise from external inputs, externally sourced data, especially STL files downloaded from the web, or model files provided by other parties in a project. The models may be damaged, requiring a repair process. Now, when you watch this video, don't be alarmed. Some users do indeed encounter this frequently, such as when another company provides a project where some models need repair, trimming, or reconstruction. Whether it's rebuild or fix it, one approach restores the original. The other outright replaces the original model. Direct reconstruction involves practical experience. Some people may not deal with model repair or this reconstruction workflow simply because they don't encounter it, right? In a normal design process, model breakage is quite rare. Next, I'll go through several case studies and share some methods I've personally used whenever model repair is needed. Within FreeCAD, there are corresponding tools and strategies to achieve the repair goal. As mentioned earlier, there are two main types of model repair. The first is additive repair. The second is subtractive repair. Additive repair means filling features like holes. For example, a hole in this model. I fill it up. This is additive repair. What about subtractive repair? For example, this cylinder here. If I don't need it, I can remove it. Or similar operations. If you have an externally imported model, you may need to use the exploded compound filter to decompose it, to break the assembly apart, and filter out each solid component for separation. Take this next example. There's a boss feature here. Suppose I don't want to keep this boss. We can use the exploded compound filter to isolate it. Then we simply filter it out. Now we no longer need it. Another scenario is when you do need the feature, but you want to change it. For instance, I might just need to adjust its original position, like moving this cylinder upwards a certain distance, or downwards. Let's assume this part is our imported model, be it an STP or STL file. The workflow is the same. First, we need to filter out the target component. After filtering, the component is separated from the main body. Then we take this pillar we need and extract it as a separate object. Once extracted, we see a hole is left behind. We need to fill this hole. Select the edges to create a surface. Okay, using the Fill Boundary Holes tool, we patch the unwanted holes on the plane. After patching, we can move the extracted boss feature using the data in this control panel to your desired location. Right? That's one method. We move it up by a certain distance and then recombine everything. This new feature is now complete. All the hole features have all been patched up. That's one method. Now, the second method is subtractive repair or material removal. We can utilize multiple workbenches in combination. Suppose in this area here, we only want to keep the geometry for the part we intend to remove. We define that material to perform the cut. But sketching directly can be a bit complex, right? If we need to perform modifications on a specific, well-defined region, we can use an isoparametric curve. Let's use this isoparametric curve. After applying it, we can extract this curve as a separate entity. Using the isoparametric curve, we can isolate and extract the contour line from the surface. For example, in this fillet area, I only want to keep a specific section. Let's say up to this point here. We only want this portion of the loop. So for this half loop, we take the current curve object and enable trimming using the split curve tool. Then we select this section to trim. For instance, we trim it at this location. After trimming here, these two line segments are extracted separately once more. This curve here is what we have after the isolated extraction. Once we have this separate line segment extracted, we can then perform actions on it, like an independent extrusion. After extruding it along the z-axis direction, we then extrude it inwards. After extruding this profile to define the region, we can then use it to trim away the corresponding part of the model. So this is a method we can use for localized regional modifications. We can trim specific areas with it. Next, let's look at a more complex case, which is this particular key is a curved key. These bosses at the bottom of the curved key all feature curvature. They are affixed to this curved surface. Now, we all know that features on a flat plane are relatively straightforward to remove. It's quite simple, actually. You can just cut them away based on that plane. However, for keys on a curved surface, removing these features is trickier. Because of the curvature, it's not as easy to handle. Especially these cylindrical columns and bosses here. They all conform to the curved surface. So, how should we approach this situation? The first method, as mentioned earlier, is to peel it away. Peel it off. But what if it can't be cleanly peeled away? In that case, we can duplicate this surface. Create a copy of the shape element. Then we can use this extracted surface and perform a Boolean cut with the original surface. After the cut operation, we can then target the filtered hole features. We can remove all of them. Remove them entirely. Next, we can also filter out the face that was based on the original object. This leaves us with a complete bowl-shaped curve body. For the next component, the task is to repair a fillet. As mentioned in the fillet repair video, for some parts with higher requirements, you might need to achieve a high-quality connection. That's the requirement. Typically, if there are no specific requirements, when we run a combo check on this area, we can see the tangency condition. Regarding the relationship between curvatures, it's AC zero continuity. To repair the surface, we still use the Gordon surface. To create a transition, a common surface connection. Once the connection is done, if we find there are too many fragmented surfaces, as mentioned before, we can use quad face reconstruction to build one complete, large surface. Take this bowl-shaped part, for example. Let's assume the common surface here is a chamfer. It's a deep, angled chamfer like this. Now suppose this surface has some damaged areas. If we try to repair specific sections of it, we'll inevitably need to create connections between surfaces. However, surface connections always face one challenge: the quality of the connection between surfaces. So, typically in this scenario, if there are multiple damaged locations, like here, damage here as well, and here, if multiple features are damaged like this, we don't recommend piecemeal repair. First, it would be time-consuming. Second, the continuity between the patched surfaces often isn't ideal. So if our goal is to have one seamless, large surface, we should consider rebuilding it. That means discarding this surface and creating a new one. For instance, with this surface that has many fragments, what we can do in this case is use this surface, extract its boundary edges, then take these 4 edges and use the Gordon surface method to reconstruct a complete surface. This way, we avoid having to patch up numerous damaged areas, which often leads to inconsistent connectivity between surfaces. This approach greatly ensures the overall integrity of the surface. Alternatively, we can use the spline approximation method, right? Utilizing sweep 2 rails to perform an approximation and generate a spline. Another scenario is when we import mesh files. Like STL files, they are mostly STL-based, correct? For example, take this simple surface. If we need to reconstruct it, the first step is to extract its original boundary edges. We can use the wires from Mesh Boundaries tool to extract those original boundary lines. Additionally, you can use the Curve on Mesh feature to draw curves directly on the mesh by connecting points. However, this method isn't very precise. If you require higher accuracy and lower tolerance, we should still resort to spline approximation. Following the same logic, we need to extract the edges from our current object. Once all edges are extracted, we can use the exploded compound filter to isolate the specific components we need. Then we can extract the boundary edges we wish to rebuild. Next, in the curves workbench, apply spline approximation to it. The same applies to this one. Apply spline approximation to it as well. Now we can see that the line we generated through spline approximation and all the numerous polylines have been merged together. Here, we can adjust its tolerance and change the continuity level. This allows us to preserve the original surface shape as much as possible. and ensure the new surface closely matches it. When we perform an inspection, comparing the original sample with the Gordon surface within a 50 micron tolerance range, let's examine the results under this 50 micron tolerance check. The maximum and minimum deviation values are largely within the allowed tolerance range. We can then tighten the tolerance further, down to 10 microns. After reducing the tolerance, we see that the overall deviation between the two surfaces is basically within a range of plus or minus 2 to 5 microns, which is acceptable. All right, so these are some strategies and methods for model repair and reconstruction. Of course, in this video, the coverage is relatively broad. I've simply shared some repair and reconstruction strategies that I've encountered in my work. I wanted to share them with you because in model repair, some issues, some more complex repair scenarios, I may not have even encountered myself. So when you're working on projects, whether you're a maker involved in 3D printing or any other related field, you might go a long time without needing to independently repair, patch, or rebuild a model from scratch. However, some users may deal with this on a daily basis, specifically model exchange between clients. It's a common challenge. In such exchanges, often during model transfers, various issues with the models can arise. Problems appear. Now, what I've covered here is by no means exhaustive. For instance, specific types of damage, like complex feature breaks, repairing and reconstructing curved surfaces, the displacement of features, or area patching, and so on. There are some issues I may not have even encountered myself. So, I'm simply sharing some of the situations I have faced and the applicable methods and strategies. I hope this can serve as a useful reference. I hope the content shared in this video can be of some help to you in your actual work and projects. That's all for this video. If I discover new methods, techniques, or strategies in the future, I will continue to share them with you. See you in the next episode.